Today we're going to spend some time talking about the central limit theorem. So we got an introduction to the central limit theorem with our dice activity. But basically what the central limit theorem is talking about is something called a sampling distribution. So if we have this population, and it doesn't even matter what the population is or what the shape is of it, a sampling distribution is when we take a large number of samples from that population, and we do it over and over again. Let's say it was just a population of people, maybe the town of Bryan or something. And a sampling distribution would be like, we select 50 of them, and then we select 50 of them again, and then another 50 and another 50. So those are our samples, and then the distribution of all of our samples is our sampling distribution. Now, if we take that sample size n, so let's say 50. So I take these 50 people from Bryan and I find whatever mean that I'm looking for, maybe their mean age. And if I continue to take samples of 50 people, so I take another 50 people and another 50 people, and I keep finding all of those average ages from each of those samples, we call that a sampling distribution of sample means. And we can find all kinds of things about the sampling distribution. We can talk about proportions, variance, standard deviation, all kinds of different stuff, which we will do throughout the semester. Now, the central limit theorem is a very powerful theorem in statistics, and it states that for any given population, and we have this mean and standard deviation, a sampling distribution of the sample means is going to have these characteristics. There are two really important things. Either we need to have a sample size of at least 30, or the original population is normally distributed. Okay, one of those two things has to be true in order for the central limit theorem to work. So the three things that we learned from the central limit theorem is the mean of the sampling distributions of sample means. We call it mu x bar because it's the mean of the sampling distribution. It's equal to mu, the mean of the population. The standard deviation of the sampling distribution, we call that sigma x bar. Our standard deviation actually gets smaller, and so it's sigma divided by root n. And the shape of a sampling distribution will approach normal. And we saw all of those things with our dice activity. We saw that the means were equal, and we saw that when we did samples, those smaller groups, we had a smaller standard deviation, and it approached normal. Even though we started out with a uniform distribution, it approached normal. So now these formulas are ones you're going to need to use. They're on your formula sheet, so they're not things you're going to have to memorize. So suppose we have standard deviation of movie ticket prices in the US is 72 cents, and we take sample means from sample sizes of 52. So what I do is I take movie tickets, I take a sample size, so 52 different movie tickets from different places, and we do that again and again. The standard deviation of the sampling distribution of sample means, that is sigma x bar. That is equal to sigma, the standard deviation of the population, divided by root n. That's just our formula. So sigma is 72 cents, and our sample size is 52. I'm just going to grab a calculator, put that in there. And so our standard deviation of the sampling distribution of sample means is going to be right about 10 cents if we round it. Okay, so you can see originally we had a standard deviation of 72. When we did the sampling means, we have a much smaller standard deviation. All right, next we've got this histogram. It is the population distribution of weights of 600 horse jockeys. The mean of the population is 116.2 pounds, and the standard deviation is 3.9 pounds. Horse jockeys are very small and light because you need the horses to run fast. So this is a sampling distribution of the sample means for sample sizes of n equals 45. So what we did is we took 45 jockeys, we found their average weight, and then we took another 45 jockeys, found their average weight, and then we plotted that. So this is what we ended up with. So our question is, can the central limit theorem be applied to the situation? And we can see it's not terribly normal, but we still can use the central limit theorem because of the sample size. The sample size was 45, which is greater than 30. So the sampling distribution's mean, so that's mu x bar, that is equal to mu, which is just the mean of the population itself, which it said was 116.2 pounds. The sampling distribution's standard deviation, that is sigma x bar. So that is sigma over root n, that's our formula. So the original standard deviation was 3.9 pounds, and we have a sample size of 45. And so we get 0.58 when you put that in the calculator. And then the sampling distribution shape, it is going to be approximately normal. We are guaranteed that. Either if we start with something that's normal or if we have sample size greater than 30, our sample means distribution will be approximately normal. All right, let's check out one last one of these. So this graph is starting salaries for law school graduates entering the workforce in 2007. This is the population. So to describe the shape of this, well, it's definitely not a normal distribution. And it's not skewed because you've got stuff, let me pull that back up so you can see it, because you have this here and here, these big spikes. So we're going to call this bimodal because we've got those two different high points. So we'll call the shape of this bimodal. All right, so now we're going to take these law school graduates, and we're going to create a sample means using sample size 25. Can the central limit theorem be applied? And the answer is no. The sample size isn't large enough. And the other problem with it is the original one was not a normal distribution. If we had a sample size of 25 and the original distribution looked like this, then we could still use central limit theorem. But since it doesn't, since it was that bimodal thing, we cannot use a central limit theorem. Okay, and in part C, consider the sampling distribution of the sample means created from this population for sample size of 50. If we do a sample size of 50, can we use the central limit theorem? And the answer is yes, because the sample size is greater than 30. Okay, so in order for central limit theorem to be applied, either the original population has to be approximately normal, or we have to have sample sizes of at least 30. And then we have that mu and standard deviation formulas. We'll be doing a lot more with the central limit theorem as we go throughout the week.